Um, in this video, we're going to learn a couple of things. One is how to use combined gas laws, and the other is that I wear jeans on casual Fridays. All right, so recall from a previous video that the various laws for gases can be combined into one where pressure times volume is a constant. That's Boyle's law. Volume over temperature is a constant, Charles's law. And then pressure over temperature, that's Guy-Lussac's law. So that PV over T is a constant, so that means the pressure and the volume and the temperature in one set of conditions is equal to the pressure times the volume divided by the temperature in a second set of circumstances. All right, so I've written up a couple of questions here to answer using this approach. Okay, in the first one here, helium has a volume of 180 milliliters. It has a pressure of 608 torr, and it has a temperature of 29 degrees C. All right, this would be in pink. This is conditions 1. And then we're going to change the pressures and the volume and the temperature. And so if the pressure is changed to 3.2 atmospheres and the volume to 90 liters, then the final temperature, T2, can be determined through solving for the unknown. Okay, so the first thing to notice that it doesn't matter what units you use for volume as long as they're the same. Well, they're not the same, so we're going to have to convert volume. The pressure units are not the same, so we have to convert the pressure units. And the temperature, of course, is not at all correct. Since the temperature is an absolute number, we cannot use a degree C ever. Okay, so, all right, so we're just going to make a list of the variables. So V1, 180 mils, is 0.180 liters. A pressure of 608 torr is going to be converted to 0.800 atmospheres. Okay, so that's what happens when you use the conversion factor of 760 torr in 1 atmosphere. And then, of course, to get 29 degrees C converted to Celsius, Kelvin, you have to add 273. So 273 plus 29 is 302 Kelvin. T1 equals 302 Kelvin. All right, now these numbers are more or less going to be the same units already. So we're going to call this P2. And V2 is going to be 90 liters. And so the final temperature, T2, is our unknown. All right, so you have to be able to do some algebra to solve this problem. Okay, so to get T2, I'm going to multiply both sides by T2. So T2, and I'm going to multiply both sides by T1. And so that's the first thing I did, just to get rid of these denominators. And now I'm going to solve for T2, dividing both sides by P1, V1. All right, and that's just 1 right there. So, okay, so I need T1 times P2 times V2 divided by P1 T1. All right, so let's see if we can figure out what's going to happen. So first is we're going to expand the volume, so that tends to cool a gas. We're also going to raise the pressure, which tends to heat the gas, but we're not going to do nearly as much. So the volume is going to expand by, looks like a factor of 100 or nearly 1,000, whereas the pressure is only going to change by a factor of 4. So we're going to predict a much lower temperature, mainly through the expansion of this gas. So let's see what numbers we actually get. All right, T1, so 302. P2, 3.2. V2, 90. Divided by P1, What is V1? Okay. So, now, looks like we're going to get a much larger temperature. Ah, yeah, I forgot. Okay. So, I'm obviously getting a temperature different than what I expect, and I forgot. I was reasoning backwards. What happens is, in order to make the gas expand its volume, we need to heat it up, just like we do with the hot air balloon. So that's why the temperature is actually going to be a very large number. All right, so the fact that I got an answer I didn't expect, then I have to think about, okay, well, was my expectation wrong, or is the answer wrong? So you look at both of them, and it says, well, the algebra looks right. So maybe the temperature is high, and then think, oh yeah, now I figured out why my reasoning went off. All right, so the numerator is like nearly 87,000 divided by 0.8 divided by 0.1, 604,000 degrees. That's huge. All right, so remember I did say the expansion of the volume is a factor of about 1,000. It's a real surprise that the temperature has to be about 1,000 times higher. All right, so that was some really large numbers there. Okay, so what about specific cases where you could work maybe a subset of this? All right, so let's look at Boyle's law problem, where pressure times volume is a constant. Let's see if we can do a little better on our reasoning skills this time. Okay, so we have 8 liters of Freon, so we're going to call that V1. And 550 millimeters of mercury, we're going to call that P1. It's changed to 2280 millimeters of mercury, so that's P2 at a constant temperature and number of moles. And so basically we could use PV equals nRT even to solve these equations. But the combined gas law is a more direct way to do it if you can remember that equation. So what is the final volume, V2? Okay, so we could convert both pressures to atmospheres. We'll still get the same answer. We could use any number for temperature. So we could say, hey, T1 equals T2 equals 100, or maybe even 1. That's easy to divide by 1, right? If you divide by 1 Kelvin, then you just have PV equals PV. So let's go ahead and just use the numbers as they are, and this time try to figure out what the final answer is going to be. So at a low pressure, okay, the gas should have a large volume. So that means this is a large volume compared to this. So we're going to expect a number of about 2 liters. All right, let's see what happens. All right, so we're going to solve for V2, which means to divide both sides by V2. All right, so P1, V1 divided by V2 equals P2, whoops, solving for V2, sorry. We divide by P2. All right, let's try it again. Divided by P2, that's equal to V2. All right, double check the algebra. All right, now we're good. So put in the numbers, P1, 550. 2280. This time we're putting the units in. You see how the units cancel? And times volume, 1, 8 liters. And we'll see what we get. 550 times 8 divided by 2280. And hey, 1.9 Not bad. Liters, right? So